Good morning. In the first half of unit, we learned about a transistor and we classify transistor into two types. The first one is a BJT and the next one is FET. In the first half, we learned the simple definition of a BJT, a construction of a BJT, working principle of a BJT, and finally different configurations of BJT. In the next half of unit, we are going to learn FET. FET stands for Field Effect Transistor. The field effect transistor is a three-terminal unipolar device that uses electric field to control the current flow. So what is a unipolar device? As we know, BJT. BJT stands for bipolar junction transistor. BJT is a bipolar device. What is the meaning of that? In the BJT section, there is an N-type. If you are assuming an NPN transistor, N-type, P-type and N-type. On the one side we are going to provide input and the other half we are going to take an output. So if you observe here, there is an N-type and there is a P-type. Here there are electrons, here there are holes. So the current flow is due to both the electrons and so BJT is called as a bipolar device since both charge carriers, electron and holes, are reason for the current flow. But whereas in a field effect transistor, here only one charge carrier, either it can be N-type or a P-type, is responsible for the current flow. So field effect transistor is a unipolar device, whereas BJT is a bipolar device. Moving on to the next point, it uses electric field to control the current. In a BJT, as we increase the input, the output current increases. As we decrease the output current decreases. So the output current is completely dependent upon input current. So we can call BJT as a current control device, whereas in a FET this is not the case. It is controlled by the voltage source. If we increase the voltage source or decrease the voltage source, correspondingly the drain current will increase or decrease. We are going to observe in detail how the current varies with the variation in electric field. Moving on, the BJT has three terminals. First one is the emitter, base, collector, whereas a FET will have a source, gate and drain. In the construction section, we are going to see source, gate and moving on. The field effect transistor FETs are classified into two types. The first one is JFET and the second one is IGFET or also called as a MOSFET. JFET is again classified into N-channel JFET and P-channel JFET. MOSFETs are again classified into DMOS or EMOS. EMOS is again classified into P-channel and N-channel. Similarly, EMOS is classified into P-channel and N-channel. D stands for depletion, E stands for enhancement. Moving on to the construction and physical structure of a JFET. So construction of a JFET is we are going to take an intrinsic semiconducting material and we are going to dope this intrinsic semiconducting material with N-type impurity. Assuming we are making N-channel JFET. I am going to dope this intrinsic material with the N-type impurities except for this region. In this region, I am going to dope with the P-type impurities. On the one half of N-type impurities, I am going to connect a one terminal and call this terminal as a source, and the other half of N-type impurities I am going to connect one more terminal and call this one as a drain, terminal D. And we have two more terminals, this one called as a gate terminal and this one is also called as a gate terminal. So internally in a JFET there are four terminals, but externally we have only three terminals. Internally they are going to connect these two gate terminals and we are going to get only one gate terminal at the output. So in conclusion, there are three terminals. This one is a drain terminal, gate terminal and a source terminal. Similarly, for a p-channel JFET, p-type impurities, this section will be the n-type impurities and this one also n-type impurities. The pathway from source to drain is called as a channel. Here the pathway is made up of N-type impurities. This one is called as a N channel. The pathway is made up of a P-type impurities. So this will called as P channel. Moving on to the working principle of JFET. For analysis, we are going to consider an N-channel JFET. The analysis will be similar for the P-channel JFET, whereas in P-channel JFET, the charge carriers will be holes, whereas here in N-channel JFET, the charge carriers are electrons. As the name says itself that the channel is made up of N-type material. In N-type material, electrons are the charge carriers. So the current is due to the electrons. Coming to the circuit diagram, here gate terminal and source terminal are short circuited and a voltage source of VDD is applied between source and drain terminal as shown in the figure. So if the voltage source is a 0, the depletion region will be the yellow one. This one will be the depletion region. It is evenly distributed on all sides. The thickness of depletion region is same on the all sides. If we slowly increase the voltage VDD and observe the shape of the depletion region changes. So let's say a voltage of 4 volts is applied across source and drain terminals. As source is taken as a reference, this will be a 0 volts. The gate terminal and source terminal are short circuited. So gate terminal will be also 0 volts. This one will be also a 0 volts. As the potential of a battery is 4 volts, the drain terminal voltage will be of 4 volts. Voltage at this particular point is 4 volts and voltage at this particular point is 0 volts. So halfway between the drain and source terminal at the center, the voltage will be half that of potential difference, which will be a 2 volts. And if you measure the voltage over here at the 1/4 of the length, it will be 1 volt. And if you measure at this particular point, it will be 3 volts. The electric field intensity slowly increases as we move from source to drain. So if you observe at this particular point, which is a 1 volt point, the N type is connected to higher voltage level and a P side is connected to 0 volts, which means a lower voltage level. So we can say that this junction, PN junction, is in reverse bias condition. In reverse bias condition, as voltage increases, the width of the depletion region increases. So for 1 volt, let's assume the width of the depletion region will be at T1. Moving on to the next point, at this particular point, N side is connected to a 2 volts and the P side is connected to a 0 volts. Now the potential difference is a 2 volts. For 2 volts, the thickness of depletion region will be T2. As we know, for a PN junction diode in reverse bias condition, as reverse bias voltage increases, the width of the depletion region increases. If you observe, here the reverse bias voltage is 1 volt and here it is a 2 volts. Hence, the thickness of depletion region over here is more when compared to the thickness of the depletion region at this particular point. So moving on to the 3 volts, here potential difference is further more. Hence, if T3 is the thickness of the depletion region, then it will be greater than T2 and T1. Hence here the thickness of the depletion region is further increased. So overall we will get a depletion region in this shape, an uneven depletion region where the thickness of depletion region slowly increases from bottom to top. Similarly on the other side also. As we further increases VDD voltage, the width of the depletion region will further increase and they will come too close to each other such that the ID becomes almost 0. So this voltage where ID current is minimum is called as a pinch off voltage. At pinch off voltage, the gap between the two depletion regions will be less. Moving on to the applications of FET. The applications of FET are similar to that of a BJT. They are used in amplifiers and they are also used as switches in electrical and electronic devices. Our next concept is comparison between BJT and JFET. The symbolic representation for a BJT of NPN type is in this way. The arrows is towards the emitter terminal, whereas in NPN type BJT, the arrow is away from the emitter terminal. Coming to the JFET, for an N-channel JFET, the arrow is away from the gate terminal, whereas for a P-channel JFET, the arrow is towards the gate terminal. Here the three terminals in BJT are base emitter collector, whereas in a JFET are gate, drain and source. Moving on to the next point, BJT is a bipolar device. As we know, BJT, let us consider an NPN transistor. In NPN transistor, the current flow is from one region to other region. So there is an involvement of both the charge carriers, both holes and electron. So the current in a BJT is due to both charge carriers, hence it is called as a bipolar device. Whereas in FET, field effect transistor, gate doesn't have any involvement in the drain current. The current only flows through the channel, which is either N type or a P type. So the current is only due to the single type of charge carrier. So FET is called as an unipolar device. Moving on to the next point, we are going to discuss the third point after fourth point. In a common emitter configuration, the collector current is approximately equal to beta times IB, where beta is the current amplification factor in common emitter configuration. Where if you observe, the output current, which is a collector current, is a function of base current, which is an input current. As we vary the input current, the output current varies. So we can say the BJT is a current control device. It depends upon the input current. Whereas coming to the field effect transistor FET, the expression for output current, which is drain current, is this one. So if you observe, both these terms are a constant. The only variable is VGS. So ID is equal to drain current. The output current is a function of VGS. Make a correction over here. It is VGS. So we can say field effect transistor is a voltage control device. It depends on the voltage, which is VGS. Moving on to the next point, the output current is approximately equal to the emitter current, whereas the output current in a field effect transistor is equal to the source current. The BJT has a high power consumption, whereas FET has a low power consumption. High power consumption results to bad thermal stability. So BJT has a bad thermal stability, whereas a FET has good thermal stability. A BJT has a higher noise level and a FET has a lower noise level. And the size of a BJT are larger when compared to the size of JFET. And the last point is we cannot interchange the terminals in a BJT. If a terminal is meant to be used as an emitter, it should be used as a emitter. It cannot serve as a base or either as a collector. Whereas in a field effect transistor, we can change the terminals of a drain and source. If we interchange the terminals of drain and source, the performance will be the same. There is no degradation in the performance of JFET.